Here's some good practice questions to get you ready for the summative on ionic and metallic bonding. I don't worry too much about the metallic bonding. It's pretty simple, right? Metals do tend to lose electrons and form positive ions, but in metallic bonding, those electrons aren't necessarily donated to a specific ion, which would be more true of ionic bonding, where there's the positive metal, that's the electron donor, there's a negative nonmetal, that's the electron acceptor, and we talk about this definitive transfer of electrons. But with metallic bonding, it's like the metal ions lose their electrons, but they don't go to a particular targeted ion. Instead, they kind of just donate all their electrons to this sea of electrons, where the electrons are kind of free to move and flow amongst all the positive nuclei, which eventually gives us some of the unique properties of a metal. So in this first question, I guess you could call it number one, the first statement is true. Metallic bonding is described as positive metal ions in a sea of electrons transferred amongst all the metal cations. So cation, just another word for a positive ion. Now that's why metals are malleable and ductile. Malleable, we can pound them into a thin sheet. Ductile, I can draw them into a thin wire. They're bendable and they don't break. Because if I apply pressure, the electrons can just kind of move, and the positive nuclei can move within this sea of electrons. It's not like a rigid crystal lattice like we see in ionic bonding, where if I apply pressure to an ionic crystal, it's gonna crack. And so this middle statement is not true. Metals are not brittle. I might say that about an ionic solid. Brittle meaning like it could crumble. No, metals can bend and change shape. The third statement is true. Metals are great conductors of electricity due to the presence of mobile electrons. In order to conduct an electric current, you need moving charges. And yes, the electrons and the positive nuclei to some extent are able to move in a metal. Number two, true or false, these are in reference to ionic solids. False, ionic solids will not conduct electricity, not in the solid form, because in order to conduct electricity, we need moving charges. Whoa, we need moving charges. And you're not going to get that in an ionic solid. The solid is a very rigid crystal structure where it's positive, negative ions that are very strongly attracted to each other. Those ions aren't moving. Now, if it was a molten ionic compound, if it's melted so that it's in the liquid phase, and liquid particles can flow, and that's kind of hard to do because ionic solids do typically have high melting points because those ions are so strongly attracted to each other. There are some that can be melted, and in that case, if the ions can move in the liquid phase, an ionic liquid would conduct electricity. Or most often we think about ionic compounds dissolved in water as being good conductors of electricity. Yes, many ionic compounds are highly soluble in water, and later on this year we'll study that a lot more. Super common. I mean, sodium chloride dissolves in water all the time, right? When an ionic solid dissolves in water, the ions separate from the crystal. So you get these positive and negative ions just kind of swimming around in the water. Well, there you go, moving charges. And so that's why they say, don't drop your hair dryer in the bathtub, because tap water has tons of ions in it, and those ions will conduct an electric current. From there, question 3 kind of just dealt with the ins and outs of ionic bonding. So we've got this model here that shows a calcium atom with 2 valence electrons, and those electrons are being donated to 2 chlorine atoms. Looks like the chlorine atoms in their outer shell have 2, 4, 6, 7 valence electrons. When all is said and done, in the final product, the calcium and both chlorine have full outer shells. That's the whole point of bonding, is that stable particles have full outer shells of electrons. And so question A, why are electrons transferred from the calcium to the chlorine? And maybe you said something about how, well, the calcium only had 2 valence electrons. And so if we're trying to get a full shell of 8, if my choice is to either lose 2 or gain 6, it's probably easier just to lose 2. The chlorine atoms already had 7 valence electrons, and so now it's easier just to gain 1. Well, here we can give both, I shouldn't say both, I should say all 3 atoms a full outer shell by transferring this 1 electron of calcium can go to 1 of the chlorines, because the chlorine can only take 1 more electron. So I'm going to need 2 chlorines so that calcium can get rid of both electrons. There could be a question that would say something like, why do I need 2 atoms of chlorine for every 1 atom of calcium? And we would say that, well, because whoopsies, I put that in there as the wrong element, didn't I? I could fix that. This isn't calcium, it's chlorine. If the question said something along the lines of, there it is, chlorine. Now, why are there 2 chlorine atoms? Well, because the calcium needs to donate 2 electrons, but chlorine can only take 1. So if I have 2 atoms of chlorine, I can make sure that both of the electrons from calcium are donated. The resulting charge then, if you lose 2 electrons, the charge is +2. And so when I think about like that balance of charge, where it's the calcium atom versus the calcium ion. Well, the calcium atom has 20 protons and 20 electrons. We're always going to keep the same number of protons. We're never changing the composition of the nucleus. That would change the identity of the particle. We're just changing the outer shell. So if I lose 2 electrons, now I only have 18. And so we think of charge as a balance between the number of protons and electrons. So when you lose electrons, that means there's going to be extra protons. The charge is positive. So on the flip side, if you gain electrons, your charge is going to be negative. Something like chlorine, the atom versus the ion. Chlorine is element number 17. So in a neutral atom, there are 17 protons and 17 electrons. But now as an ion, I keep the 17 protons, but each chlorine will gain an electron for 18. Oh, there it is, -1. When you gain electrons, you're gaining extra negative charges. So your overall charge will be negative. And then finally, part C, it's the ions that are more stable. And I think that's a misconception, that people think that, there's a charge, that's got to be a bad thing. No, it's a good thing. All of the ions on the periodic table, I should say all the atoms, need to fix their outer shell, except for the noble gases. They're the only elements that are stable when they're neutral. Everybody else needs to fix the outer shell in order to obtain a full octet. And so here it's the charged ion that's more stable. They've finally obtained their full outer shell. Question 4 is kind of Coulomb's law. We can use Coulomb's law to gauge the degree of attraction between oppositely charged particles. That could mean the nucleus versus the electron cloud, or here it could be the attraction between oppositely charged ions in an ionic compound. Just like Coulomb's law, there are 2 factors that we look at. Number 1 is the magnitude of the charge. So when I have ions that have higher charges, that's going to create a stronger attractive force. So between the lithium chloride and the lithium oxide, the oxygen's got a higher charge, so that's going to create a stronger attraction. And then the next thing that we would look at would be the size of the ions. We want small ions that can pack real tight together. Between the chlorine and oxygen, oxygen is a smaller atom, and so that would also leave me with a stronger attractive force. In this case, the number one thing we would have looked at is the magnitude of the charge. And so because the oxygen has a higher charge, this is going to be the stronger attractive force. If I had particles where the charges were the same, then for sure the tiebreaker would become number 2, which has smaller ions that can pack more tightly together in their little crystal lattice, and that would create the stronger attraction. All right, then we got to get into writing ionic formulas and understanding how they're put together. So I love 5. How many ionic formulas can you write given these 1, 2, 3, 4, 5 ions? Well, number 1, an ionic compound has to have a positive ion and a negative ion. There were only 2 positive ions on the list, just barium as a +2 and potassium as a +1. So those are my only choices to start my ionic compound. They always start with a positive ion. Then I just kind of went down the line with the negatives. So bromine is negative, a -1, and oxygen is negative, that would be a -2. Phosphorus is a -3. So I could make barium bromide, barium oxide, and barium phosphide. And then I can kind of do the same thing with the potassium. Potassium bromide, potassium oxide, and potassium phosphide. When you're writing ionic formulas, you got to be a freak about the charge. So you got to know how to find the charge on your periodic table, which obviously you can use when you're taking the test. And so you should have all these charges marked in. Then you can either be a balancer where you try to make these charges add up to 0, or you can be a crisscrosser. Either is totally fine. I like number 6. An ionic compound has the formula X3N2. Is metal X more likely to be an alkali metal or an alkaline earth metal? So I decided to find the charge on metal X. You always work from the backwards, or from the back end of the compound, because there are no negative ions that have multiple charges. So if I look up nitrogen, it's -3 for life. No other options. So if nitrogen is -3, and there are 2 of them in the formula, if I multiply, that gives me a total negative charge of -6. So that means I got to get a +6 out of my metal X. Well, there are 3 atoms of metal X. So if each of them were a +2, then 2 times 3 would give me the +6. So the charge that I'm looking for is the +2. Which group is more likely to have a charge of +2? I get that like the overall charge coming from the positive ions is a +6, but each ion of metal X is a +2. And the group that's always +2 are the alkaline earth metals. I like that one. Number 7 and 8 are just some great practice on writing formulas and naming compounds. You will obviously have your periodic table, and you will have access to that chart of polyatomic ions on page 98. So the chart is linked in the assessment, and you can just have your book open to page 98 if you want to. Potassium is a +1, and then I look at the ending, chlorate. That ATE ending means I gotta look it up. ATE is a polyatomic, ATE and ITE. And so I look up chlorate, it's a -1. +1 -1 is neutral right away, so you slap the symbols together and it's a done deal. Now with calcium phosphide, the IDE is the regular element on the periodic table. So calcium is a +2, phosphorus is a -3. In blue, you could be a charge balancer, trying to get these both to add up to a +6 -6, which gives me a neutral charge overall. Or you can be a crisscrosser. Crisscross the 2 charges, and you don't bring down the plus or minus. but you get the same formula either way. Now, the only time that the crisscross might fail you is on part C. Manganese Roman numeral 4 just means that manganese charge is +4. It's a transition metal, so it can have different charges. We can't just find the charge by looking at the periodic table. So the Roman numeral is a good thing. It's just telling me the charge on the manganese. The IDE oxide is a regular oxygen. Now, if you're a charge balancer, you're going to say, okay, +4 -2, I'll just take 2 oxygen, and that gives me a +4 -4. Done deal. If you're a crisscrosser and you crisscross the 2 and the 4, then you just got to say, wait a second, these formulas need to be reported as the simplest repeating pattern of the crystal. So if I have a subscript of 2 and 4, I would simplify that. So the true formula is just MnO2. Kind of the same thing would happen in part D. Copper 2 carbonate with the ATE ending. I need to look it up. It's the polyatomic CO3. Now you got a +2 -2, and so right there it's neutral. I don't need to crisscross. You don't need parentheses if it's just one group of carbonate. If you put them in, it's fine. It's not wrong. But again, if you were a crisscrosser and you crisscross a 2 and a 2, well, then you should simplify that to a 1-to-1 ratio. Now, when I get to part E, aluminum oxide, I get that it ends in IDE. There's just a handful of polyatomics that do end in IDE. It's like cyanide. Hydroxide is super common. But most people kind of get this one because they know that oxide is on the periodic table, just oxygen. So when they see like hydroxide, like, oh, that's a little different. It's OH. It is really common. We'll use a lot of hydroxide this year. So you look it up. It's -1, and the aluminum is +3. So you can crisscross, you can charge balance, but this time I need the parentheses around the OH group to show that it's 3 groups of hydroxide. And if you wanted to write this out like a really long way, you could write it as like aluminum +3, and then there's hydroxide, hydroxide, hydroxide. But eventually these formulas would look a little funky and they'd take up a lot of space. So we want to show 3 groups of hydroxide. And then it should be neutral. The aluminum was +1. Each hydroxide is -1. It should give me a total charge of 0. When I write the names in number 8, sodium is always in the group that's +1. So this thing is just sodium phosphate. I don't need a Roman numeral because sodium does not have multiple charges. And then when I see the PO4, here's the deal. These ionic compounds only have 2 parts to them. There's the positive ion and there's the negative ion. They have 2 words. And so you're not going to have like sodium phosphorus oxide. There's never 3 words to these things. It's 2. It's always a metal, non-metal. And if you see there are 2 non-metals, like, oh, PO4, I would guarantee it's a polyatomic. So if you write sodium and then you see 2 non-metals, look it up on that chart. I bet you'll find it. Now, B is a little goofy. Ammonium NH4 is the only polyatomic that is positive. And you also kind of get a giveaway by it being in parentheses. If something's in parentheses, then it's like a group, and that might make me think, ooh, that's weird. Better look it up. Ammonium and then sulfide. Just regular sulfur turns to sulfide. Now, lead and chromium do need the Roman numeral. We need the Roman numeral for transition metals, tin, and lead. They're the particles that typically have more than 1 charge, and a lot of that comes from the unstable, kind of crazy d orbitals. So transition metals, tin, and lead, I need the Roman numeral. Now, this is just lead oxide. And then to find the Roman numeral, we balance the charge. Oxygen is always a -2. There's only one of them, so the lead must be +2. Chromium nitrate is D, but we've got different forms of chromium nitrate in the lab. Actually, chromium is one of my favorite metals. Solutions of chromium make different colors. They're really pretty. All right, so I know this is some kind of chromium nitrate. So we work from the back to the front. Nitrate is a -1. There are two groups of nitrate. So the total charge from the negative ions is a -2. There's only one chromium, so it's got to give me a +2. So the +2 becomes my Roman numeral, chromium 2. The last one is just potassium sulfate. So again, if I have potassium, sodium, if it's a metal from group 1 or group 2, and it always has one particular charge, like the boron family with boron and aluminum, you don't need a Roman numeral. If the metal is coming from one of those groups, that's always +1, it's always +2, it's always +3. It's transition metals, tin and lead, that need the Roman numeral. So not with sodium, potassium, aluminum, calcium, no Roman numerals. But then the SO4 is the sulfate, wherein B, just regular sulfur, and that was the sulfide. Notice too that, like when you see the symbol formula, there are never Roman numerals in the formula. The Roman numerals only come in the name with the words. And also note that the Roman numeral is not the subscript. So when I see something like manganese 4 oxide, it's not Mn4O. Sad face. No. The Roman numeral is not the subscript, it's the charge on the metal ion. Those are maybe some of the common boo-boos that I've seen over the last few weeks. And then finally, these are some great questions. Just, do I really understand what's going on when these ions come together and bond to form compounds? Number 9 has another metal X that bonds with oxygen to form the compound. Oopsies, not oxygen. It's bonding with chlorine to form the compound XCl3. What will be the formula when X bonds with phosphate? Okay, so first we got to find the charge. So I've got XCl3. So chlorine, I know, is always a -1. And there are 3 of them, so that gives me a total charge of -3. Okay, so then there's just one X. So X has to be a +3. Well, now I can just write the formula of X and phosphate. So if X is a +3, phosphate is going to be one of those polyatomics. So I just look them up on a chart. PO4 is phosphate, and its charge is, oh my gosh, lucky day. Its charge is -3. So it's done. XPO4 +3 -3. I like questions like number 9, like, do you really understand ionic bonding? Can I figure out the charge on an ion when it's bonded to one particular element? And then could I bond that metal X with something else and figure out its charge? The charge will stay the same. It's a great question. Kind of similar with number 10. Okay, metal X bonds with oxygen. There's the oxygen to form the compound X2O. Okay, so oxygen is always a -2. There's only one, so the total negative charge is just -2. There are 2 atoms of X, so each must be a +1, so that I can go 1 times 2 and give me a total charge of +2. So the charge on the X ion is a +1. Each is +1. And so sometimes people will put +2. Oops, we want like the individual charge on the X ion. I get that overall we need a +2, but individually each X is plus 1. 1 times 2 is 2. Okay, so now B is the stumper. If the X ion contains 28 electrons, what is the identity of metal X? Okay, so the X ion is formed after that metal had lost 1 electron, because I know the charge is plus 1. So the X ion is formed once I lost 1 electron. And once we lost that 1 electron, we ended with 28 electrons. Okay, but I want to know the identity of the element, so I need to know how many electrons are in like a neutral atom. If I know how many electrons are in the neutral atom, then I know how many protons are in the neutral atom. And I can look up then the atomic number on a periodic table. So the trick is that the 28 electrons is for the ion. That's after I had lost 1 electron. So the original neutral atom had 29 electrons. Then I can say there would have been 29 protons, and element 29 is copper. Isn't that tricky? Obviously, the most common boo-boo is to say nickel, which is element 28, but we just forgot to take that charge into consideration. It didn't say that the atom had 28 electrons. The charged ion had 28. And so then I have to backtrack a little bit to think, okay, well, the ion is plus 1, which meant that it had lost an electron. So if I put that electron back, the original had 29. 29 electrons, 29 protons. That's copper.